I'm an engineer and researcher at HashMatter. We are working on privacy-preserving networks, peer-to-peer networks. And that's basically a subset of what we're going to talk about today is coming from this work. So yeah, we're going to be talking about privacy in peer-to-peer networks, and we're going to focus on distributed hash tables. And the reason for that, I'm gonna explain a bit later on. But in general, it's a very good kind of protocol to introduce this theme, and also it's been used widely in many interesting projects that are out there. So we're going to start by talking about what's the future we're building, and then jump into what kind of privacy-preserving primitives can we start deploying and building, and then where to go from here. All right. So I will start with a question. So how many of you here are somewhat part of building a future in which peer-to-peer decentralization is actually mainstream? Trying to do that at least. Okay, perfect. Yes, I'm very excited about that future as well. Very excited, especially because of all the. It's probably one of the few ways I see that we can actually build an ecosystem, a technology that can actually be as human as possible, and very intellectually stimulant as well, to be thinking about protocols, be thinking about technology, but also the social part of the interactions with different peers, different nodes, different people. And another thing that actually brought me to this world of peer-to-peer and decentralization was the idea that we don't really need any central authority kind of mediating communication and collaboration between people. And that was very interesting back in the days, and it's still very interesting for me. And the idea that without having to rely on a central authority, we can actually achieve what we all probably nowadays are very concerned about, which is privacy. So the idea that we don't have anyone kind of monitoring and having access to our interactions, our social graph, our social patterns, we can actually achieve a degree of privacy that it's what we as a society deserve. But as we start kind of digging a bit more deep and kind of trying to really figure out what's happening and trying to understand what's the privacy sort of a model of peer-to-peer systems, we start seeing that the picture is a bit different from what we really want and what we want to improve from where we are at this point. And that's exactly what I'd like to be talking about today, because if many of us are actually trying to build the future of technology, I think that also sort of brings a bit of a responsibility onto our kind of shoulders in a way, right? So we want to build technology that is good for society, and it's much better than what we have now. And that's basically where sort of the starting point. So that's basically the starting point of all this sort of a conversation. So we're going to be talking about privacy in distributed hash tables, and the reason to focusing on distributed hash tables is that I believe it's a very interesting sort of a protocol, a peer-to-peer protocol that it's easy to understand how it works. It's very, very efficient. It's been shown to work very well in large scale with many projects that we've got running nowadays. And it also shows a bunch of interesting privacy threats, privacy sort of attack surfaces. And that's basically what we're going to be focusing on. So I'm not going to be trying to explain what a distributed hash table is, but I'm just going to go through it very quickly. So the idea of DHT is that we can build a completely decentralized peer-to-peer overlay network, right? In which the different peers in the network can collaborate and contribute with each other in order to create this sort of a decentralized key storage, key value storage. The content is hashed and published to the network. The different peers agree with each other where to store the content, where to retrieve the content from, and so on. So just a very interesting thing about distributed tables, before trying to explain a bit how it actually works, is that it can be in a very efficient way, be used as like the scaffolding, the infrastructure for many of the decentralized apps that we will probably try to build in the future, and we're already building nowadays. There's already a bunch of interesting kind of networks, a bunch of interesting protocols, a bunch of interesting projects implementing different DHTs. And then there's already also a bunch of applications being built on top of the DHT. So basically, we can see it as a scaffolding or as an infrastructure of distributed apps. So the real, like, very, very fast, very quick, going through how does the DHT sort of a protocol works. The idea is that the unique ID domain of content and peers sort of overlap in a way that everyone in the network agrees that the peer with ID X will be most likely responsible for storing the content with the ID X, right? So that's a very kind of overall idea. And the idea also is to have a protocol that can be as scalable as possible. So it's impossible to keep an index in every single peer of who owns or who has which content. So basically, we end up resorting to a collaborative protocol, and we ask the peers around us who is most likely to have the content that we're looking for. So basically, the idea is that a lookup initiator, when looking for a content with an ID E, is going to look into its own routing table, finger table, which basically has the direct connections to a subset of the peers of the network, and it's going to ask, okay, to that one, to the one of the finger table peers, okay, do you know where or who's most likely in your routing table to have the content that I'm looking for? And he's going to basically answer with, yeah, most likely D. If D doesn't have, the peer D doesn't have the content, at least it's going to be closer than me. So, and then eventually, if we keep following this protocol, we will converge into finding or not finding the peer which is responsible for the content. So this kind of works for both storing and retrieving content from the network. So eventually, the initiator got the IP address or the address of the node that is most likely to have the content he's looking for. And then they basically start and then they basically can exchange content, data, they can communicate, whatever. Basically, it's a routing protocol, very simple but very efficient to resolve sort of indexes in a completely decentralized protocol. So this is very like overview of how DHT can work. There's a bunch of different other details in the different implementations, but this kind of sets the ground for what we're going to be talking about throughout the talk. So one thing, I believe it's like an overarching idea of all this protocol is the idea that we can think of the peers as being in the middle of a crowd communicating with each other, right? So people are basically shouting at each other, trying to learn who is where and how. So basically, there's a lot of information being shared by peers so that they can actually achieve their own goals, because we need the peers to collaborate because we don't have the full view of what's happening in the network. So that's like a very interesting idea that we're going to be exploring later on. So one of the interesting things about these is that DHTs are very interesting kind of constructions to allow us to build these key value storages in a completely centralized way and in a way that is very scalable, because we don't need to keep all like indexing locally. But then also like basically the same thing that makes, or the same properties that make distributed hash tables a very, very good fit for peer-to-peer and decentralized systems is also the exact same detail and property that will make it very, very not as good as we would like in terms of privacy, right? So that's exactly what we're going to be talking about. And the problem, this is another point, is that the problem with that is these sort of vulnerabilities bubble up to the application level, right? So if the protocol is vulnerable to metadata leaks or privacy vulnerabilities, most likely the application level will be as well if the application developers are not either sufficiently aware of the problems and try to figure out a way to actually go around the vulnerability problem. So this is basically the sort of the problem that we're facing here. And just like, instead of going through the details of how are we actually leaking privacy data in distributed hash tables, I'd like to just do a series of sort of a thought experiment. So let's just imagine that we live in a world in which peer-to-peer is like basically everywhere, right? So we have as many users using client-server centralized services as peer-to-peer, and DHTs happen to be one of the sort of a most popular sort of a constructions for building these networks. And on top of this kind of peer-to-peer infrastructure, we've got three different applications: the Insta, the YTube, and the site. So let's see what might happen and how they would work on top of DHT. So this is basically like, imagine in a world where we are actually somehow successful from these kind of conferences and stuff. All right, so the D site. So this is actually an application in which users can store and retrieve web page content. So basically what we would call web content, right? In which the URL is the ID of the root of the web page. Well, this might be a very familiar kind of setup for many of you that you've already used in many of the projects that are out there. And it's a very interesting kind of construction, a very interesting way to use and leverage peer-to-peer technologies to store your own personal content and let other people to access it in a decentralized way as well. So now let's imagine that Bob adds his own personal website to the network, and just because it's a peer-to-peer network, he ends up caching the content in his own device, right? So he just publishes the index to the network, the DHT, and caches the content in its own device. What's very interesting is that if we start thinking that Bob is caching the web page in his own laptop and then moving around, right? So basically going to Berlin, going to London, going to anywhere. What kind of data are we actually leaking from these? Like, well, how can an adversary kind of take advantage of the fact that Bob is storing content in his own laptop and moving around? So basically the idea is that if someone, even a curious peer, is constantly sampling where are the providers of this specific content, and this specific content is Bob's webpage, he can actually gain a lot of information on where the Bob might be. And this is basically based on the IP address of the provider of the webpage. So the interesting thing is that, and you can see this already kind of working as I think the timestamps are wrong, but everything else should be fine. So this is actually an example of to do this on IPFS. So it's very easy. There's no like magic on it. I was storing my own webpage on IPFS. And basically, every time you would try to find the providers for this particular content, you would get a different IP, which can map or not map to my physical location, right? So basically, we get this very cool kind of map in which you can see that in April, I was somewhere in London. Then 29th of April, I went to Tenerife, very cool. And then went back to London and now to Berlin. So basically, the idea is that you are, just by storing and just by caching your own content, you're leaking a lot of metadata of your own information. So this is the kind of things that usually people retweet 1,000 times, super scared of what Google is doing to us, right? Without us knowing. Oh, they're tracking our position with GPS and whatnot. So this is exactly what we can also do with DHT, for example, if we're not careful enough. So the other very interesting case is it's also very simple. Again, the Insta, it's nothing else than a photo application, right? On top of a photo sharing and storage application on top of a DHT. If we are really like naive on about how are we sort of storing and kind of controlling how the data is shared amongst peers, the problem is that whenever Bob actually requests for someone's photo, you will have to rely on the network's peers' information for actually get access to it. So basically, every time Bob requests for Alice's photo, he will most likely have to ask peers around him, hey, do you have or do you know anyone who has Alice's photo? And that's basically, again, another kind of vector to leak a lot of metadata about people's behavior, right? So we really don't want to have a kind of system in which people around us might be able to monitor, track, and like gather information on who am I looking at, whose pictures am I looking at or interested on, or who is my social graph, or what is my social graph interactions with people and whatnot. So the last case is this DUI tube. So basically the idea is more or less the same. We've got a streaming platform, a storage platform on top of a DHT for videos. And again, each video has a unique ID. You can store your own video, you can stream live, or you can even just fetch some content on the DHT, which is a video, right? And the interesting thing is that anyone can actually replicate the video by, for example, pinning. Maybe it's a jargon you guys are familiar with. So basically the idea that anyone can add a sort of a replication node for a particular video. And this is very interesting and opens yet another attack vector, which is not only for DHTs, but peer-to-peer networks in general. Peer-assisted CDNs, content-to-distributed networks, are another example of constructions that leak a lot of information like this. But let's imagine, again, in this hypothetical scenario that there's Bob lives in a country in which there's this rogue government, right? That they're very smart, very into peer-to-peer networks and whatnot, and they actually cache, set up a bunch of nodes for caching video about opposition videos, right? So basically the idea is that they can actually get a very good picture of who's potentially accessing the data. And this can actually start to, the government can actually learn from its citizens who is actually against their rules or against their ideology, against their politics, and then we can only imagine what a rogue government can actually do with that. And it is the same thing with the corporations trying to understand their customers, track content consumption and whatnot. So this is yet another kind of interesting attack vector. Just by caching content and providing content to the network, you're actually learning what the people who are requesting content from you want. I think that's very simple and kind of straightforward to understand what's happening. So the idea here in these three cases is that, unfortunately, if we as system designers, as system developers, are not careful enough, we're actually leaking a lot of metadata, a lot of information on what the users of the network are doing, right? And in this case, encryption, end-to-end encryption will not help at all, because the problem here is that we're leaking information not through the content of the messages, but rather for the fact that we are contacting a particular set of nodes. And I think the overarching idea, in my opinion, is that unfortunately, the future in which we open up the door for this kind of attacks is no better than what we have nowadays, right? So nowadays we've got central authorities, central corporations, kind of basically monitoring many of our actions through their platforms. But what we're opening up door is, if we're not careful enough, is to make it so that everyone in the network, so basically everyone can know what you're actually doing. And surprisingly enough, you don't need, or the adversaries don't need that much resources, that many resources to actually perform these attacks. in a very effective way. So yeah, that's the idea, is that we centralize systems, we disclose our information to one entity, decentralized potentially to everyone, and that's not a better future that we're looking for. So, okay, so that's more or less the kind of to set the stage for what we're going to be talking next. The idea now is to, all right, so this is very interesting, a lot of interesting problems here to solve, but let's try to kind of structure, how can we think about the privacy in peer-to-peer systems, right? So I really like this approach of having a granular definition of different privacy goals. So we can have initiator anonymity, in which, in the DHT, for example, given a lookup request, if a node receives a lookup request, he or she doesn't know who the initiator was, but still can continue the protocol to go forward. The same for target anonymity, in which, given a lookup initiator, you don't know, and the packet, you don't know who is going to be the end goal, but you still can carry on with the protocol. There's lookup and linkability and replication interest as well. So the idea here is that you cannot, or adversaries in the network will not be able, and this is another goal, will not be able to link different lookups and interest with the fact that a peer is replicating its content. So this is basically like a bunch of like granular goals for us to achieve and to think about when to create the protocols to enhance privacy. And the interesting thing is that we want to really have low overhead. So this is where it makes everything hard, right? So we could just use a mixnet and we're fine with it, but mixnet adds a lot of latency. Mixnets might add also a lot of scalability and also a centralized problem. So the idea here is that we want to achieve these privacy goals while at the same time keep low latency, which is very important for DHTs and DHT application level. We want to keep the system as decentralized as possible and scalable as well. So the interesting thing, in my opinion, here is that these are very hard problems. So, okay, just if we remove all the privacy concerns, and many of you guys know it's very hard to get a healthy, scalable peer-to-peer system, DHT, working for thousands of people. So when you add these privacy goals, it makes it even harder. So that's like the interesting and intellectual stimuli to it. So when talking about security, when talking about privacy, we always talk about the threat model. So can I give a bit of a context? What kind of adversary are we dealing with, and what kind of what's like the playground here? So in this talk, and basically on the protocols we're going to be talking about, we're actually concerned only with local adversaries, which perform passive and active attacks and controls up to 20% of the nodes in the network. So what this means is that we're concerned with an adversary that is able to spin a bunch of nodes in the network, place it in random or even arbitrary places in the DHT, and then is basically sniffing all the requests and all the traffic that goes through the nodes, and basically just trying to infer as much information as possible with all the information taken from those nodes. And by passive and active attacks, then again, passive attacks is basically just getting all the data that is going through the network, storing that data, and then an active attack is actually actively changing the routing table so that it can actually make the passive attacks even more efficient. We're going to see how that works. So another thing is, like, many of the questions that sometimes come out is like, how about the global adversaries, right? So how about this idea of a rogue government or sort of a corporation, or that have enough resources to basically sniff the whole network and try to understand, like, basically have a full picture of what's happening in the network. So unfortunately, it's very hard to deal with those kind of adversaries if we want to maintain low latency. It's also kind of, if we think about the hypothetical future in which there are millions of peers part of the same network, I believe it's also going to be very hard to have enough resources to do that. So I think for now we can leave that aside. That's, I think, a complete different ball game, and maybe mixed networks would do the game in that case. But that's basically not for this. It's not in this sort of a context. So basically, I'm not so much interested about what NSA or RUG government would learn about me, but more of what my neighbors and what small corporations or what basically anyone in the network can learn about me, right? So that's basically the idea here. All right, so another thing that I really like to kind of think when talking about privacy preserving networks and whatnot is to see it from a developer perspective, right? So as a peer-to-peer application developer and designer, how can I actually improve the privacy of the users, right? So based on our goals and based on our threat model already defined. So how can we either change the DHT or build a sort of a layer of privacy on top of the DHT so that we can achieve those goals under this threat model? So that's basically what we're going to try to answer the rest of the talk. And by the way, feel free to kind of interrupt me, raise your hand, and just ask questions. I think that's will be even easier for me as well. So yeah, that's the idea. And we're going to be talking about these for actually three sort of a set of protocols. Delegated encrypted requests, plausible deniability through noise, private information retrieval, and oblivious transfer, and then a very specific kind of protocol called from the academia called Octopus DHT lookup, which unfortunately has never been developed and deployed, but it has very interesting capabilities and super interesting. So we're going to go through like very quickly through those and understand how can we actually build the sort of the components and the modules to give the developers the superpowers to provide their users with privacy on top of a DHT, for example. All right. So one more thing that I'd like to just kind of get a bit of context here, especially for the most technical kind of people. The idea is that all the sort of protocols and mechanisms that we're going to be talking are actually sitting in between the overlay network, routing network layer and the application level. So we're not talking about routing or forwarding your traffic through some Tor network or some mixnet outside of the DHT. So the idea here is, can we actually build a sort of a layer on top of the DHT to add some or enhance the privacy of our users? So that's more or less what we're going to be talking about here today. So yeah, let's start with the delegated encrypted requests. This is a very interesting kind of way of saying this. So one example of these types of protocols is, for example, onion routing, right? So, and the interesting thing is that when we think about onion routing, usually we think about Tor. But in this context, what we're concerned with is like onion routing on top of DHT. So in a way that instead of just making a lookup request, you can actually pick a bunch of random nodes in the DHT and relay, encrypt the packet, which has basically the lookup information, and then just route this packet through the relay kind of circuit that you've constructed. So the interesting thing about this, so the idea is that you're not making the lookup request yourself. You're basically delegating someone else to do the lookup request for you. And in between this sort of a delegation, you're actually building a secure, encrypted kind of path using the same basically mechanisms as Tor is using, for example. So the cool thing is that no relayer will actually be able to learn who is the initiator of these packages. So again, instead of just making the get of triggering get content ID request, we're actually gonna first of all select a bunch of DHT nodes. And by the way, these are nodes which are in the DHT. We have not only a routing table but also a relayer table. And the way this relayer table is populated, again, this is a very interesting problem just by itself. Tor, for example, has that problem nowadays. What they use is basically a centralized directory of all the relays used and trusted. So that's yet another very interesting problem. There's a really cool paper called Shadow Walker, which might be one of the solutions to do this on top of a DHT. So that's yet a lot of things to think about when it comes to these kind of protocols. But anyways, so the idea is that the initiator will select a random, as anonymous as possible, set of relayers, and then basically derives a set of Shared keys for symmetrical encryption encrypts the payload in layers so that the first layer, basically the core of the onion package can be only decrypted by the exit node. And then the second layer from the core is actually from the before last, or the relayer. It's going to be decrypted by the relayer before the exit node and so forth. So the idea is that once we get this onion packet with the request payload, which is basically what the payload, or which has information about what the exit node will request. We need also the relayer, addresses, relay, public keys, etc. And then we start actually, we forward this package to the first relayer. It will decrypt, get the next relayer information routing, send to the next one, so forth to the last. The last actually realizes upon decrypting the package that is the exit node, gets the request payload, and basically the delegation part comes from here. So the R2 node is actually the one responsible to do the DHT get contact ID. We can use previously built packets that can be kind of used by the exit node to send the response back in an anonymous way as well. So basically what we got here is a protocol which does not rely on Tor, does not rely on anything else but DHTs, and that gives us a set of interesting privacy properties. So this actually, you can already see this working on top of libp2p and IPFS. So basically, you can already there's a video, and there's also the code is, I think, well commented, at least in this particular one, where you can actually use p3lib, which we're going to be talking about later, which implements basically some of the modules or the packages needed for routing through to use onion routing on top of DHT, and it's like very compatible with libp2p, so you can contribute, check how it's going, and also kind of take a look at it. Yeah. Another interesting thing, okay, I think I already mentioned this, but I just want to say this very quickly. Again, we're using an onion routing on top of the DHT rather than using Tor or any other anonymous transport layer below. And the reason for that is because we want better latency, I believe. Then again, I'm not talking without measuring anything, and that's yet the sort of work we're doing at HashMatter is really to try to understand how does this kind of protocol behave in terms of latency, and also how to add the incentives on top of this protocol in order to make sure that the different relayers, the different nodes are actually going to kind of relay and behave as expected in this protocol. So there's a lot of interesting avenue here. The cool thing about putting this protocol on top of the DHT is that it gives a lot of flexibility to the application developer. Basically, imagine a developer who is like developing this Insta, for example, that we've seen before. Probably he wants to use onion routing for a set of requests. Probably he doesn't want to use onion routing because it just adds latency, and the requests they're doing, the users are doing in some cases don't really need any privacy. So you can really kind of plug and play not only this specific protocol, but also other protocols. So that's like one of the interesting things. And there's no like usability problems or anything. So I think that's a very interesting kind of thing. So how do you actually measure privacy in a system like this? Is there enough entropy when it comes to if there's no like enough relayers and enough sort of onion routing packets going forward, being forward, back and forth? Also, how do we deploy and develop a scalable, decentralized PKI infrastructure? And again, I think the incentives are a very interesting kind of topic to be working on. Actually, again, I think in terms of incentives, it's yet another very interesting research topic because, well, cryptography, it's kind of free, but privacy is not. So someone has to pay for, if we're not using the altruistic kind of model in this case, as for example, Tor uses, someone has to pay for the work done for the peers around you to help you to have privacy in peer-to-peer networks. So that's a very interesting kind of research topic that we're trying also to kind of work on. All right, so the second kind of set of interesting protocols to add privacy to peer-to-peer networks, we can call it plausible deniability through noise. Again, this is a very kind of large subset of protocols, but we can actually focus on a very kind of narrow and a very kind of simple way of seeing this problem, and it's going to be easy to kind of go through some other ones. So 5 minutes, oh my God. Okay, so I'm going to be very fast now. Okay, so the idea about the plausible deniability through noise is that we build protocols that make it impossible for relayers and for peers to be sure about things, right? So basically, I'm a node, I receive a request from another peer that I know his IP address, I know his identity somewhat, but I'm not 100% sure whether if it was him or not who initiated these requests. So this kind of adds to a certain degree some privacy, sort of a privacy layer on top of it. So the idea is that, yeah. So I'm going to go through very quickly now, and one example of that is the coin flipping request delegation, which is very kind of straightforward, simple protocol to add this plausible deniability. So the idea is that every time you kind of create, you kind of make DHT get value lookups, for example, to several nodes, the different nodes who actually receive the request will flip a coin. And that flip coin will, if we get heads, we're going to actually create a new lookup request, which is exactly the same that I got. If not, I will just proceed with the protocol itself. So what this is going to actually make is that without this coin flipping, basically, you know that this request is coming always from the initial, sort of the initiator, the original initiator of the lookup request. Whereas with the coin flipping, you never know because some of the nodes in the middle of the request might have flipped heads and started a chain of new requests. So basically, eventually, you lose information about who actually was the original initiator, right? So this is a very simple protocol. Again, very hard to measure, very hard to be sure that things are actually working as supposed. What if none of the relayers are actually flipping the coin? But just to give you an idea of how this kind of plausible deniability works in this case. And the interesting thing, yet again, is that we can build all of these on top of the DHT. We don't need any kind of weird, like any other kind of platforms to get these kind of privacy kind of properties in place. There's much more sophisticated protocols using this concept of plausible deniability. And then you can also, interesting thing is that can also be, you can also use plausible deniability of caching. So let's say that I'm caching content because I'm interested in it. But what if I cache X more random content what if I cache more content that I'm actually interested about, right? So for each of the files that I'm actually interested for some reason, because it's my website, I'm also caching 10 other websites, right? So the point is that when some peer asks me for a content or for some file and I have it, because I'm just also basically caching random stuff, not only the things I'm concerned with, it also adds sort of a plausible deniability in that case. So this is what I'm talking about here. So very simple, very interesting kind of set of protocols. Again, how to measure privacy, random noise versus useful noise, and how to ensure that actually the nodes behave as expected. Again, this is the incentive problem, which is very interesting in these kind of cases. Okay, so very, very quickly. The other thing which is a bit more complex and it adds a bit of overhead is to organize, instead of being like a routing table, instead of we having a routing table per node, we actually have a routing table per quorum of nodes. And this quorum of nodes is like a set of nodes which agree upon a routing table. And the interesting idea is that you can create a bunch of like private information retrieval and very interesting multi-party computation protocols based, for example, on threshold signature schemes, right? In which you actually make a request, this particular quorum, and no one in the quorum is going to be able to, if up to a certain security degree, of collusion, no one in the protocol will be able to actually understand what's the query that you're making. So that's very cool. And you can actually be using this in the DHTs. There's actually a couple of very interesting papers about robust DHTs in which you use this quorum for attacking spam or protection against spam, and then you can actually use this privacy as well on top of it. Very interesting. Again, you can build all of these on top of the DHT. The Octopus DHT lookup is, I'm just going to go very fast, very quickly on this. So the whole idea is that, okay, what if you, instead of asking for a particular ID, or if you, instead of asking to appear, okay, do you have these content ID, or do you know anyone which is closer to it, we actually ask for the full routing table, right? So that's kind of, this is a very simple private information retrieval mechanism in which you're not actually saying, okay, I'm interested in this content, but you're rather, okay, give me everything, and I'm locally gonna pick the node from where to kind of route next. But the problem with this is there's this range estimation attack in which if the attacker owns a bunch of nodes, he can eventually converge over time, right? So the idea is that I'm controlling these two nodes, and I know that the second request that one of my nodes got is closer to the content that I want. So you can kind of converge to the final destination, and you get a lot of information out of it. So what Octopus DHT does is to request a full routing table, have multiple disjoint lookup paths, and dummy queries. And it's very interesting because it's one of the most interesting, at least for me, papers that I've seen about how to get initiator lookup privacy on DHTs. But the assumption is that all the active adversaries, so the ones that are tweaking the routing table to make the passive attacks more effective, have to be removed from the system. They also present a protocol, which I don't have time to go through, but it's very interesting. I would definitely recommend you to take a look at it. And then there's also the restricted routing topology. I think it's this idea of if, as far as you just send your request to the people you know and trust, you're good to go. And then they will, based on the small world network principle, they will eventually route for where you want. Also very interesting. I think, like, for example, Scuttlebutt somehow uses this principle. I don't want to be saying anything wrong. Anyways, then we can get sort of a very interesting table. And this is not 100% correct, but it just gives an idea of the different sort of privacy goals that we had against the different protocols. And if we think that as a developer, we can actually plug and play, just as we do, for example, with P2P modules, we could actually plug and play friend-to-friend routing or onion routing or random replication to the different sort of needs of the app developer. So that's basically what we're trying to do with the P3lib. So basically, P3lib is this sort of a idea of creating sort of a toolbox for engineers and sort of application developers to enhance privacy in peer-to-peer networks. So we're trying to not only do the research for what are the protocols that fit in between the application level and the routing layer, but also try to develop the protocols primitives that can allow the developers to use it. So one example is the P3lib Sphinx, which is actually the all-purpose onion routing implementation, which is very compatible with libp2p. Basically, the idea is that to have everything compatible with libp2p so that everyone can use. The plausible deniability for DHT lookups using the coin flipping is also being developed now, and the specs are being fleshed out. Oh no. Okay, it's gone. I think that okay, it makes sense. I think I've been. I think this is the best.